All right, here we go. Last chapter. Finally. All right, we're looking at what? Thermal properties of matter. Let's start out by looking at the atomic model. Now, most of you that's probably had chemistry, most of you have, should understand that there are phases in which matter exists. Of course, solid, liquids, and gas. And there's also actually plasma. Could be our fourth phase of matter. Plasma is highly energetic particles or molecules or ions, okay, is how we look at plasma. Of course, gases are when it's in a gaseous, when an object or a material is in a gaseous state, the molecules move randomly, and gases do not have a definite shape or volume, so there's no definite shape or volume for a gas. A liquid, however, does permit motion, but it's not as random and not as fast as gases, and liquids have a definite volume, okay, but no definite shape, okay. And then solids have a definite shape and a definite volume. So they have definite shape and definite volume. Now they do say they can be compressed somewhat, but still for the most part they have a definite shape and definite volume. Now when we look at objects, materials, and in particular we look at the periodic chart of the elements, we need to understand something. We talk about atomic mass and atomic mass number. The atomic mass, and again this is a review from chemistry, is the sum of all your protons and neutrons in an atom. We call that the A number. And of course atomic mass is established on the carbon-12 isotope, and that's a misprint. It should be carbon-12. And of course it comes out to be exactly 12 atomic mass units, 12 AMUs. And here they define what 1 AMU is in mass. Notice it's 1.66 times 10 to the negative 27 kilograms, which, by the way, is very close to the mass of a proton and a neutron. Very, very close, okay? Hopefully that jumps out at you there. And so, basically, when we look at the molecular mass of an atom, of course, it's the sum of all the sum of the atomic masses of the atoms that form that particular molecule. Now, here we see the atomic mass numbers of some various elements. Notice hydrogen's 1, helium's 4, carbon is 12, okay? Nitrogen, 14. Now this is particular isotopes of carbon and nitrogen. 12 and 14. Oxygen 16 has an atomic mass of 16, 20, 20, and so on, okay? All right, so I think that's self-explanatory. Now, in order to measure out atoms, we have to use something called the mole, which was developed by Avogadro, and it's based on Avogadro's number. And so what we discovered, or he discovered, that 1 mole of any particular substance, if it's water, if it's, well, let's just stick with elements. Let's say lithium or beryllium or copper or silver or gold, has 6.02 to the 23rd atoms or particles within that 1 mole. And you say, well, now, how does that make things equal? Because it doesn't matter what the material is. If you take 1 mole of any particular element on the periodic chart, then guess what? It's going to have that number of molecules. Well, that makes it very unique in that now we can compare different substances to each other and still be on the same playing field. In other words, a mole of copper can be equal to a mole of aluminum, okay, based on that principle. And folks, it is true and it works because we are able to go in the laboratory and produce compounds with very high accuracy, high precision based on this concept. Now, of course, monatomic gases such as helium, and again, it does depend on the substance, would be 6.02, but if you're looking at a diatomic gas, then it would be twice that for 1 mole. So if you got a mole of a diatomic gas, it'd actually be twice Avogadro's number, okay? All right. And here they're showing you some various monatomic gases. Of course, there are actually 7 diatomic gases. You have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay, those are the 7s. Bromine and iodine. Bromine's a liquid and iodine is solid, but iodine easily sublimes, and bromine evaporates very easily when it's exposed to air. All right, now, so being that Avogadro's number is 6.02 times 10 to the 23rd per mole, now you do that in mole to the -1, that just means per mole, then we can find the number of moles by doing what? By taking the number of particles and dividing it by Avogadro's number, okay? So this is how we find the number of moles based on the number of particles. So if you have, a million particles, how many moles do you have? Well, divide a million by 6.023. 6.02 times 10 to the 23rd, and you get the number of moles, okay? All right, now we can also do this. That being said, we can find the number of moles this way, since the relationship exists between the atomic weight of substance and the number of moles you have. And you say, well, how do I know if I have a mole of a substance? Well, go to the balance, take it, and for example, if you need a mole of carbon, then take carbon, go to the balance, weigh out 12 grams, and guess what? Or 12.0111 grams, or whatever the atomic mass is. We just say 12, close enough. Then you have 1 mole of carbon. So, that being said, then if we can take the mass and divide it by its molar mass, and we can find the number of moles. And just like I said, if we have 12 grams of carbon, and we know that the molar mass is 12 grams per mole, then we have 1 mole of carbon. Okay, it's that simple, all right? And you probably did that in chemistry. Now, let's look at volume, okay? Now, remember, regardless of the phases of matter we have, we're always going to have volume, okay? Well, plasma's a little different. Of course, plasma is matter, so it would have volume. I mean, if you looked at the volume of the sun, what is the sun? It's just one big chunk of plasma, okay? It's a big plasma reactor, all right? Now, yes, it's through nuclear fusion, but it's actually in the plasma state, all right? Now, all right, so when we look at volume, how do we determine and get the unit, the unit for the liter? Well, it's actually a derived unit, okay? And I think I did this derivation back in 201, and I won't go into it, but here they show you how we derive the liter. That 1 liter is actually what? It's actually 1 decimeter cubed, or 1 meter cubed is equal to 100 centimeters cubed, and so forth, okay? And so we derive this. And if you take a box that is 1 decimeter by 1 decimeter by 1 decimeter, then you have the same unit as the liter, okay? And I don't want to get into all that derivation again, okay? All right, let's look at the atomic model of an ideal gas. Now, one thing we've learned about gases is that the gases are directly proportional to their average kinetic energy per atom, okay? And we can define this way. We can say that the temperature is equal to 2/3 of the kinetic energy average divided by the Boltzmann's constant. And that's how we can find the temperature of an ideal gas, just by using that equation there. If we know its average kinetic energy, and we know Boltzmann's constant. And Boltzmann's constant is 1.38 to the -23rd joules per Kelvin. And yes, you need to write that down, and yes, you need that for your final exam. On your formula card, okay? Now, all right, so, and again, where's the 2/3 and all that come from? I don't want to get into all that derivation. I do with my calculus-based physics students, but I'm not going to with y'all. Now, so we look at the thermal energy of an ideal gas. Notice that the thermal energy of n number of atoms is equal to what? Well, the number of molecules times the kinetic energy average, or basically saying what? 3/2 the number of molecules, that's what that N stands for, times Boltzmann's constant times the temperature. And by the way, the temperature always has to be in kelvins, always, okay? That's how we can find the thermal energy of an ideal gas. Now, we can also turn around and, well, okay, there it is for you, Boltzmann's constant. So notice it's directly proportional to the temperature. Notice this and this are on the same plane, directly proportional. So what does that mean? That means as the temperature goes up, the energy goes up. I think that's commonsensical, isn't it? Now here's showing you the molecular speeds of various gases. It's pretty interesting. You look at the molar mass of a particular gas and you see that its molar mass is directly proportional to its, the speed of a gas is directly proportional to its, or inversely proportional to its molar mass. Because if you have a very low molar mass, then it can have very high root mean squared speeds. And here they show you how if you take the kinetic energy average and divide it by the sum of all the kinetic energies and then the number of molecules, notice what we get. Notice how things begin to cancel out and we wind up with what? We wind up with that right there, 1/2 m. We find out that the root mean squared speed is equal to the velocity squared average speed, and that's the average speed of a typical atom. Or we can do some substitution and use Boltzmann's constant, and that's not the only way we can find the root mean squared speed, because you got to realize something, that molecules, that energy is always going to be conserved, but that you've got, and you say, well, why is it root mean squared? Because you've got molecules can move in 3 directions. You got X, Y, and Z, okay? Now, so we can find the root mean squared speed of a particular molecule of gas, or any particular atom. It doesn't just have to be a gas, but typically we're looking at ideal gases here. 3 times Boltzmann's constant times the temperature in Kelvin divided by its mass. Okay, that's one equation, one way to find it. Okay, and again, this is just a summary of that. And there's other equations that we'll get to here in a little bit. Now, how do we? Now we're building to something. We're building to the gas laws. Okay, so we understand now temperature, how we can find temperature. We understand the relationship of volume, what volume is. Volume is basically the length times the width times the height. It's always going to be in meters cubed when we're doing these problems. When we're looking at the energy of gases especially. And what about pressure? Well, pressure, of course, is the force per unit area. And again, I don't want to get into a lot of this because we covered it in 201. But anytime you look at a given area and look at the force applied to that area, you have pressure. So there's your pressure equation back when we were doing pressure in 201 last semester. Pressure is defined as the force per unit area, and that is 1 Pascal. And 1 Pascal is 1 Newton per meter squared, okay? And you do need to remember that Pascal is the pressure unit for pressure, and it's abbreviated PA, right there, PA. Now here's standard atmospheric pressure, 1 atm is equal to 101.3 times 10 to the third kilopascals, or 101,300 pascals. We always write it that way right there because it's 10 to the third. And those are not the only units for pressure. In America, we use 14.7 pounds per square inch. We could also say 760 torr, or 760 millimeters of mercury, 1,013 millibars, 29.92 inches, okay, of mercury. So there's different units of pressure. They all represent 1 atmosphere of pressure. So here we see then what? That the force net on a force net produced on a particular material, the walls of the container. Notice how we get this. We take, to find the force net, we take the second force minus the first force. Well, look, y'all, if you substitute your equations in, notice what we get. Notice we get pressure 2 times area minus pressure 1 times area, or in other words, factor out the pressures, and it's what? So the force net on a container will be equal to what? The area times the change in pressure, okay? Very easy, isn't it? Sure is, all right? Now, what is a vacuum? Well, a vacuum is any space in which the pressure is less than the atmosphere. If you look at insulated windows are basically under vacuum. Well, to some degree. They actually do put argon between the panes of glass, but I think it's very low pressure argon. It's actually in a vacuum, okay? All right, so but anytime you remove air from something, then you have what is called a vacuum. And of course, a perfect vacuum is 0 pascals, but that's basically impossible, because how are you going to remove every single molecule from a container? It's impossible, all right? So gauge pressure then is the difference between the actual pressure and the atmospheric pressure. That's how we define gauge pressure. So what does this tell us then? Pressure is directly proportional, so we know that kinetic energy and temperature Average kinetic energy and temperature are directly proportional. Well, guess what? Pressure is proportional to temperature, but it's inversely proportional to the volume, okay? And pressure is also proportional to the number of molecules. If you have more gas molecules, then you should have a higher pressure, okay? Why? Because you're adding molecules to the container, all right? But it's inversely proportional to the volume. Well, what does that mean? Well, okay, think about a bicycle pump. When you push down on the plunger, you're decreasing the volume in the cylinder of the bicycle pump, but you're increasing the pressure, aren't you? Inverse proportionality. And of course, those of you that's had chemistry know that that is Boyle's law. That pressure and volume are inversely proportional. So we look at the ideal gas law, and of course we know the ideal gas law is PV is equal to nRT. Well, we can also write it this way. nRT can also be written the number of molecules times Boltzmann's constant times the temperature. We can also write it that way. And by the way, do not forget that your temperature has to be in kelvins. We can also write it this way. PV is equal to the number of moles times Avogadro's number times Boltzmann's constant times the temperature, or just simply PV is equal to nRT. And by the way, we're going to find out here in a minute that PV, pressure times volume, is the work done, okay? So the work done on the gas, we can find it looking at the pressure times volume. And please remember that the R constant, when we are doing these particular equations that deal with pressure, ideal gases, and work, notice this is work, y'all, then look, that right there, R has to be 8.31 joules per mole Kelvin. You cannot use the 0.0821 liters atmospheres per mole Kelvin. You cannot use that constant, okay? Because here we're looking at the energy of the gas, okay? You cannot use the other gas constant, okay? So, hence, we see then that PV is equal to nRT. Notice they give you the values for each one. So if we're actually looking for the kinetic energy involved, remember that PV is equal to work, which is equal to kinetic energy, and so forth, all right? Then you've got to use the 8.31 joules per mole Kelvin, and please, please, please make a note of that. And of course, pressure has to be in pascals, and volume has to be in meters cubed, okay? And of course, I've already told you temperature in Kelvin, so you must remember this, okay? Very, very important. All right, now, so let's go ahead and look at the ideal gas process, of course. How do we define an ideal gas? Well, of course, you got to have a fixed quantity. You got to have a well-defined initial state, initial volumes of course, pressure, temperature, and volume. And then, of course, there's a well-defined final state of final pressure and temperature and volume. Hence, we can write the ideal gas process this way. We also call this the combined gas law, okay? Combined gas law. Now, combined gas law, we can write it that way, okay? And you say, where does that come from? That comes from the combination of Boyle's law, Charles's law, and Gay-Lussac's law, okay? That's where it comes from, all right? Because Gay-Lussac is pressure and temperature is directly proportional, and Charles's is volume and temperature directly proportional, okay? So you combine and all three, and that's what you get, okay? Now, when we look at PV diagrams, very interesting. We can learn a lot from PV diagrams. When we look at these, we can determine what's going on, what kind of process is actually occurring if we look at a PV diagram. If you decrease the actual pressure, if pressure decreases, then guess what? Volume has to be increasing. And so what you should see here is an inverse relationship there, all right? And so that's what they're going to show you on this next page. Well, I thought it was, but anyway. So if you increase pressure, you're decreasing volume, which is inverse proportionality. And of course, that is Boyle's law. Now, what about the different processes, thermodynamic processes? Well, whenever you have a constant volume process, notice what your PV diagram is going to look like, all right? If you have a constant volume process, that's what it looks like. And by the way, there is no work done here, no work, all right? No work here because the volume is not changing. You have to do work, in other words, for it to change the volume. So there's no work, then there's no changing volume. This is called an constant volume process, okay? Constant volume, is it isoket, is that right? Okay. And then isobaric process is one in which the pressure remains constant, but you do work on the gas by changing the volume. How do you do work on the gas? Well, you could add energy to it, okay? You keep the pressure constant, but you increase the volume, okay? All right, and so again, you can add energy to that, and they're showing you put a fire on it, okay? And this is called an isobaric process. Isochoric, I think, is constant volume. Yeah, isochoric. Isochoric. I had a memory lapse there, okay? And then isobaric is constant pressure, okay? Pressure doesn't change, but the volume does, so you have to do some kind of work on it, okay? And then you have isothermal, where the temperature remains constant, but you do what? You do what is called an isothermal compression. In other words, you compress it very quickly and the temperature doesn't change, okay? And so you keep the temperature constant. This is an isothermal process. And so when we look at constant temperature processes, notice that that the pressure is equal to nRT over V, which is what? Basically saying this is constant, the temperature is constant, that's a constant, number of moles are not changing. But notice what is, the volume is changing, okay? So there's an inverse relationship here between what? Between the pressure and the volume, and this is during an isothermal process. So notice you create a hyperbola, not a parabola, but a hyperbola, okay? And you see these isotherms, different isotherms for different temperatures, okay? All right, isothermal. So there you go, there's an isotherm showing an isothermal process, all right? Now, so let's put all this into some equations. So we know that if you remember from first semester 201 that the work done on an object is the force applied through a given distance, the change in distance. And here we look at force. Force is what, since we're talking about gases, is pressure times the area times the change in distance. And so what do we wind up with? We wind up with what? We wind up with work, the work done by the gas, okay? Now if you remember, distance times meter times meter squared is what? Volume, right? Meters times meter squared is volume. So what did they do? They distributed the A through there, didn't they? And so we can write this on an isobaric. Now this is for isobaric, constant pressure, not changing pressure. If it's changing pressure, we have to do an integration, okay? But we're talking about constant pressure. And so constant pressure, notice that it is the pressure times the changing volume. Notice that pressure, which is you say, well, how in the world do you get a joule out of that? Watch, pressure is what? Newtons per meter squared. Volume is what? Times meters cubed. All right, cancel. What's a Newton meter? A Newton times a meter is a what? It is a joule, all right? Look at there how that works out beautifully, all right? Okay, so we move on. Oh, and again, that's just talking about how we can, you can actually take the integration, or you can do the, you can actually do the rectangle method there to find it. Okay, here you'd have to integrate it, okay? Take the area on the curve. All right. So the first law of thermodynamics says what? That the change in thermal energy is equal to Q minus the work done on the gas. So the thermal energy only depends on its temperature. We can write this change in thermal energy as what? Of an ideal gas to be what? Change in thermal is equal to what? We've already looked at these. The number of 3/2 times the number of molecules, Boltzmann's constant times the change in temperature, or 3/2 times the number of molecules times the R constant, which is 8.31 joules per mole Kelvin, and then times the change in temperature, which is in Kelvin. So for adiabatic processes, what do we mean by adiabatic? Adiabatic means that we do not add any heat to the process. In other words, Q is 0. So anytime you have an adiabatic process, no thermal energy is added to the process. Typically occur very rapidly, okay? An adiabatic process is one that occurs very rapidly. In other words, you've not had time to add any thermal energy. And you say, what do you mean by adding thermal energy? Like sticking a torch to it or putting ice around it and removing energy, okay? It doesn't occur, okay? So adiabatic compression raises the temperature of a gas, okay? So absolutely, if you compress a gas, the temperature is going to go up. Now, all right, so thermal expansion, let's change gears now, and let's get into some more physical things, looking at solids and liquids. So if we look at thermal expansion of a volume, it's a very simple equation. It's the beta constant, which is the coefficient of volume expansion, and you have to have a table with those on it. It's a constant times the initial volume times the change in temperature. Now, the change in temperature here does not have to be, it is not supposed to be in Kelvin, it's supposed to be in degrees Celsius. Okay, it's supposed to be in degrees Celsius, all right? All right. All right. Okay, and of course here the same thing goes for change in linear, except you use what? the alpha coefficient, which is the coefficient of linear expansion. And by the way, you can use that one if you multiply. You can use the linear expansion here if you multiply it times 3. So 3, this can be written this way, 3 times alpha VI delta T. You can actually write it that way too, all right? Okay, if you know the alpha coefficient, all right? There's linear, and of course your units can be, they can be in either meters or they can be in centimeters. It does not have to be in meters, okay? All right. Now, I know they're saying K to the -1. That should be Celsius to the -1. That's a little bit deceiving. You say, well, why do they do that? Well, actually, the change, if you look at the change in temperature on the Kelvin scale, it's the same as, in other words, if I say I'm at 200 Kelvin and I go to 100 Kelvin, well, that's a difference of 100, isn't it? Well, it's also a difference of 100 degrees Celsius, okay? So it actually should be Celsius. That, I mean, it works, yes, but it's a little bit confusing, okay? And so notice they give you for alpha, for, notice this one here, it's 3 times. Multiply that times 3, and that's what you get. You see that? Look, multiply this one times 3, look at there, boom. Multiply times 3, multiply times 3, okay? And then notice for volumes, all you have is volume, okay? There's no linear, huh? Okay? Of course, these are empirical formulas. Water is very unique. A substance. I thought I'd just leave this in here real quick because water expands. Notice that its expansion rate changes as the temperature changes. Notice that it's very high. I'll say it's high. It's higher at 0 than it is at 4 degrees, okay? This is why ice will float, because the volume of water expands at freezing. Its volume expands, okay? And that's why ice will float, because it lowers the density, okay? And that's why. And a lot of that has to do with the hydrogen bonds in the water molecule, okay? All right, let's quickly look at specific heat. Specific heat of material, very important property of materials we need to understand, because it can help us to understand what the material will do when we apply energy to it. Of course, it's easily found. The mass times the specific heat constant, the symbol for that is C, specific heat, times the change in temperature. And again, here temperature can be in Celsius. It does not have to be in Kelvin. I know they say 1 Kelvin. Well, that's 1 degree Celsius. 1 Kelvin is 1 degree Celsius, y'all, because we know that what? To find the Kelvin temperature, you add 273 plus the Celsius temperature, don't you? Yes, well, that's the same as saying 1 Kelvin, all right? Okay, so we can find that, and of course that unit is going to be joules. The units of that is joules, y'all. Okay, it is joules. All right. And you say, well, how do we get joules from there? Well, if you have to look at specific heat, all right? So notice the specific heat is the number of joules per kilogram degree Kelvin or degree Celsius. Notice lead has a very low specific heat. Water has a very high specific heat. So what does this mean? Okay, if you think about it, have you ever wondered why you can set a piece of steel out in the sun and come back an hour later and it's pretty hot, isn't it? But if you set a glass of water out there in the sun, or a bucket of water that say has the same volume as the steel, notice that the water is not near as warm as the steel is. Well, guess what? Because steel has a much lower specific heat value, meaning what? That it takes less energy per kilogram to change its temperature. Okay, let me say that again. It takes lesser energy per kilogram to change its temperature. Whereas water, it takes a tremendous amount of energy in joules to change 1 kilogram of it to 1 degree Celsius, okay? That's why it takes pools, when you fill up a pool, it takes a while for them to heat up, okay? And of course here they're talking about fog over a body of water. Now let's look at phase changes. Now, so having to understand that the phase of a material depends a lot on its specific heat, doesn't it, okay? Or it's related to it to some degree. But one thing about phase changes is that phase changes do not involve a temperature change, okay? And that's the unique thing about a phase change. So actually you go through 5 phases here, taking ice, say ice at -10 to steam at, say, 120. There's actually 5 phase changes here, okay? Notice how you go from -50 to 0. Notice it flattens out. Notice there's no change in temperature. Then you go, once you get it all melted, it goes up to 100, and then it flattens out. No change in temperature till you all get it to steam, and then you heat it up to whatever temperature you want to heat it up to. So there's 5 changes there. I said 5 phase changes. It's really not 5 phase changes going from solid liquid to a gas, so it's actually 3, okay? But it's 5 steps, and you have to do 5 calculations, okay? All right, so we need to understand that, of course, there's a melting point of any material. Melting point is when it becomes a liquid, freezing point when it becomes a solid, and of course you have phase changes, and once it reaches its melting point or freezing point, it is what is called phase equilibrium, okay? All right, now, when you look at a temperature at which a gas becomes a liquid, that is the condensation point. So you take a liquid and return it back into a, gas and turn it back into a liquid. That's condensation. And of course, vice versa, when you boil it, you change it from a liquid into a gas, okay? All right, 1 second. Got to take a quick pause. Okay, sorry about that. All right. All right, now, of course, that phase change is called the what we call the heat of transformation, or the phase change, heat of fusion, heat of vaporization. Notice they use Q and they use these brackets here. Well, notice the heat needed to melt or freeze, and of course if it's to melt, you're adding. If it's to freeze, you're taking away. And to boil or condense, again, if you want to boil it, you're adding. If you want to condense, you're taking away. And notice that there's no temperature involved, okay? No temperature involved, very important. And notice that sign is very, very important. You have to keep up with which way you're going. If you're adding, it's positive. If you're taking heat away, it is negative. All right? Very, very important. So you need to keep up with that, all right? But notice our equation is what? That the Q for fusion is the mass of the substance times the constant, latent heat of fusion, and QV is equal to the mass of the substance times the latent heat of vaporization. And again, that's a constant that you have to look up on a table. Okay? All right. And then here's some common latent heat of fusions and latent heat of vaporizations and their melting points and boiling points, just to kind of give you an idea of what we are looking at. Man, look at the latent heat of vaporization for lead. Wow. To vaporize lead, that's a tremendous amount of energy. Okay. And of course, evaporation. Evaporation is a process in where you, again, take a liquid and you turn it into a vapor. Now, why is this important? Because it requires energy. That is why we sweat. That's why you go to some of these places like Gulf Shores, Orange Beach, and go up to these restaurants and they got these fans outside blowing water, a fine mist of water on you, and you kind of get that cooling effect. Well, why? Because in order for the water in the air to evaporate, it takes energy for that to happen. And so the energy is removed from the air somewhat, and it produces a cooling effect, okay? The energy is removed from the air around you to evaporate the water vapor, the water mist, okay? All right, calorimetry. Calorimetry is a way in which we can measure heat or energy, I like to say, being transferred between systems. Now, the Q net, of course, is always going to be equal to Q1 plus Q2, which is equal to 0. Why? Because the law of conservation of energy says so, that the Q in should be equal to the Q out, okay? Or the addition of the two should be equal to 0, okay? And here we see a summation of the equations. And again, remember, we know where we get our Q, and we get our latent heat of vaporization and latent heat of fusion. And now let's look at specific heat of gases. Now, gases are a little bit different in that we have to consider the process that it is going through. And so if we look at a constant volume process, notice that the specific heat or the thermal energy of a gas is based on the number of moles times the specific heat for a constant volume. Now, constant volume process times the change in its Kelvin temperature. And here we see, notice right here, the number for a constant pressure process, then the specific heat, and by the way, this CV is what we call molar specific heat at constant volume and molar specific heat at constant pressure. Okay, but we still get in that unit in joules because it's energy, okay? All right, and so here we see some CPs and CVs of some various gases. Notice it's different from volume. Notice it's higher for pressure. And of course it's joules per mole Kelvin or degrees Celsius. Okay, same difference. All right, notice it's higher for pressure than it is volume. Okay? Notice that. And notice what it is for diatomic. It's a little bit higher. Okay? And then what about triatomic? Okay? All right. Neat, right? Okay. And then really quick, heat transfer, there are, of course, four basic mechanisms of heat transfer, one of which is direct contact. Another is what we call energy is transferred by bulk motion of molecules with high energy, like we see here in this picture. And then we see energy transferred by electromagnetic radiation, okay, which is what we call radiant means, by radiant energy. And then here we see energy transferred by the removal of molecules with high thermal energy, okay, which deals with evaporation. So how do we define conduction? The transfer of energy through direct contact, okay, and of course if you increase Q, then guess what? The length of the rod should increase. If you decrease, if Q increases, the temperature difference between them causes an increase in the length of the rod. However, if you chill it, then it will shrink, okay? And so we look at the rate of heat transfer for material for cross-section area length. So notice this now, it's a little bit different. Now notice this is joules per second, isn't it? Well, hey, a joule per second is a watt. And watt is power. Well, that's not what we're looking at. We are looking at the rate at which heat is transferred, okay? So they tell you K is our thermal conductivity constant. Of course, the area divided by the length times the change in temperature. And of course, they tell you what your units for K are. Very important you write those down. And here they show you some thermal conductivity values for, notice these are all solids, okay? All right, well, except for that one. That one's air, okay? All right. All right, and of course, convection, we have transfer of thermal energy by motion of a fluid, and it can be a gas, or because gases are fluid, or it can be a liquid, and this is a very good demonstration here. And then radiant energy is where it's transfer of energy by electromagnetic waves, okay? Electromagnetic waves or energy, and we can look at the rate of heat transfer by radiant sources by taking the emissivity constant, like, and then we're talking about like a light bulb, okay, or the coil of an electric heater, times sigma, that's the Stefan-Boltzmann's constant, and there's the value for it, times, and so those two right there are constants, times the area, and notice it's times the temperature to the fourth power, meaning what? That you take the temperature and multiply itself times 4 times, okay? All right, and that's it.